The Fine Bubble Industries Association, or FBIA, was established to promote the international standardization of fine bubble technology. Bubbles in liquids are visible to the eye when they are large in diameter, such as bubbles from the air diffuser in a water tank, or the bubbles in carbonated beverages. The presence of smaller bubbles just tens of microns in diameter can be confirmed by white turbidity, which shows that bubbles are scattered within the liquid. When such turbid liquid is allowed to stand for a certain amount of time, the liquid becomes clear. However, this does not mean that there are no longer any bubbles in the liquid. Although not visible to the human eye, the liquid still contains extremely tiny bubbles, smaller in diameter than the wavelength of light. These bubbles are called ultrafine bubbles. Ultrafine bubbles can be made visible to the eye by irradiating them with green laser light. Light tracings are not visible in normal water, but become visible in water containing ultrafine bubbles, confirming the bubble's presence. Ultrafine bubbles smaller in diameter than the wavelength of light cannot be measured by a conventional optical microscope or even by a scanning electron microscope. However, various novel methods for measuring these bubbles have recently been developed by corporate laboratories, universities, and other institutions in countries such as Germany, the United States, and Japan. These methods include a Brownian motion observation method that tracks the bubble's Brownian motion. A dynamic light scattering method that irradiates the ultrafine bubbles dispersed within a liquid with a laser, monitors the fluctuation of the light scattered due to the bubble's Brownian motion, and then calculates the bubble size distribution using a Stokes-Einstein equation. A laser diffraction and scattering method that measures the angular distribution pattern of the scattered light intensity. An electrical sensing zone method that measures the volume of ultrafine bubbles and counts the bubbles. And a resonant mass measurement method that distinguishes solid particles from gas particles using a MEMS resonance device. These methods make it possible to detect large numbers of ultrafine bubbles in a liquid. Together with the development of measurement technologies, significant advances have also been made in the technology for generating ultrafine bubbles. A variety of ultrafine bubble generating methods have been developed, such as a pressurized dissolution method that pressurizes a gas to create a supersaturated solution, then rapidly decompresses the solution to generate fine bubbles and ultrafine bubbles. The fine bubbles are then separated out by a flotation process. A high-speed swirling liquid flow method swirls gas at high speed to generate large numbers of fine bubbles and ultrafine bubbles, then separates the fine bubbles by a flotation process so that only the ultrafine bubbles remain in the liquid. And there's also an ejecting method. As companies and universities around the world continue to gather quantitative data and develop new applications, significant progress in this field can be expected in the near future. As both measurement and generation technologies have progressed, scientific research and the development of industrial applications for ultrafine bubbles have also moved forward. Highly interesting and promising results have recently been reported regarding practical applications. Excellent results have been obtained especially in the cleaning field. When cleaning highway rest area lavatories, it has been confirmed that urinary calculi are effectively removed. And application in the parts cleaning processes of factories reduces environmental burden through significant water savings and reduced wastewater. Automated cleaning is another application, such as for the pipes of water heaters for recycling bath water, improving both convenience and cleanliness. Studies are also being conducted in a variety of other fields. For example, in the field of environmental protection, ultrafine bubbles are used to improve the performance of water purifying facilities and to achieve better water quality in septic tanks. They are also used to purify seawater by enhancing oxygenation in summertime. In the field of agriculture, ultrafine bubbles are being used on a trial basis to wash ginger in a mechanized washing system. And in the field of aquaculture, ultrafine bubbles are being used to remove parasitic worms from farmed fish. A study is also underway using water with ultrafine bubbles to clean salt-encrusted wall surfaces. It has been observed that the ultrafine bubbles generated between the solid surface and the crystallized material adhering to the wall promote crystal exfoliation. Ultrafine bubbles are also being used in the manufacture of semiconductors and solar cells, including the application of ultrafine bubble technology for separating solar cell wafers and for cleaning silicon semiconductor wafers. In food processing, new applications of ultrafine bubble technology are being introduced throughout the food industry.
Whichever gases you want to use, you can produce the fine bubble. Since air is the safest and the cheapest gas of all, air bubbles have the high potential to be applied to food and beverages. Carbon dioxide gas has been used for the beverages such as beers or fizzy drinks. You may be able to add new functions or values on the products. Other functions you can expect are to add fragrances to the food by fine bubble. We have already developed the mayonnaise that contain fine bubbles in the collaboration with the food company. By adding nitrogen, we could successfully reduce the calorie of the high-calorie mayonnaise per volume without changing flavor or taste. Additionally, we could add other attractive functions, for example, antioxidant function on the mayonnaise. Like this, fine bubbles have been used and developed as a novel food additive.
Because ultrafine bubbles are extremely small, they do not surface with buoyancy, and it has been confirmed that ultrafine bubbles are retained in liquids for longer than 6 months due to Brownian motion. The characteristics of ultrafine bubbles allow various aromas to be added to the bubbles, and many different types of gas can be trapped in the bubbles, functions that hold great promise for application in diverse fields such as foods, beverages, cosmetics, chemicals, and medicine. And in the field of agriculture, ultrafine bubbles are being used to accelerate vegetable growth. Early harvesting has been confirmed when using ultrafine bubbles on lettuce and other crops, indicating that ultrafine bubble technology can help to increase agricultural production efficiency, a benefit of global importance. Additional research is continuing for the practical application of ultrafine bubbles in a wide range of fields. Although significant progress has been made developing ultrafine bubble measurement and generation technologies, and their use in various applications has already begun, the terminology and definitions of fine bubbles and ultrafine bubbles have not yet been clearly established. In this regard, a three-layer system of standards is being considered, with general principles and terminology standards as first-tier standards A, fine bubble characteristics and measurement as a second-tier group of standards B, and specific industrial applications as the third-tier group of standards C. By first establishing the necessary ISO standards, a robust market can be developed so that the world can begin enjoying the benefits of this new technology. To ensure a uniform global system of standards, for Basic Standards A will establish the definition of common basic elements of fine bubble technologies, such as the term fine bubbles, fine bubble sizes, and category classification through fine bubble density distribution to describe the types of fine bubbles. By establishing international standards for such characteristics as the types of liquids and gases and the bubble retention time in a liquid, those working in this field can focus on further development using a common language. The principles of measurement and analytical technologies currently used, as well as conventional measuring equipment and analytical instruments, can be utilized for measuring fine bubbles. However, in order to perform accurate measurement and analysis, appropriate storage, transport, and preparation is necessary that takes into consideration the characteristics of fine bubbles. Measurement Standards B will specify procedures for appropriate storage, transport, and preparation so that anyone can correctly perform measurement anywhere at any time. Specific Industrial Application Standard C will specify the fine bubble application technologies for the specific fields of industry in which they are likely to be used. Thus, it is necessary to clearly define the specific conditions and effects of each application in which fine bubble technology is used. International standards regarding fine bubble technology are indispensable to the creation of a robust market for this technology, and it's considered that the development of such ISO standards would be of global benefit. We encourage everyone involved in this field to work together with the Fine Bubble Industries Association for the further development of fine bubble technology through the proposal and development of international standards for fine bubbles and ultrafine bubbles. These international standards for fine bubble technology are proposed by the Fine Bubble Industries Association in accordance with the JISC Top Standard Scheme.